Okay. Welcome to another session, folks. Uh, in our previous session, we were discussing about the N-gram model. Now, the purpose of discussing N-gram model was not to actually delve deep into N-gram models, because that's a entirely different course in itself from what I understand, which is a typical NLP course, natural language processing course. So as part of the natural language processing course, one would deal with n-grams. Of course, logistic regression is also something that we deal with when we do NLP. But the objective of the n-gram session was to drive home the point that probabilistic modeling is not some esoteric stuff that you learn in school and college that has no application at all. Because most of us feel that when we learned probability, we always had this in mind that, okay, fine, I'm learning independence, I'm learning conditional probability and whatnot. But what sort of practical use do we have for all this? That's something that that has always grappled us when we learned these concepts in school and college. So one of the reasons why I took up the n-gram for discussion was because I wanted to introduce the idea that, look, all these concepts are not mere esoteric stuff that you learn in school and college, but has a lot of practical applications too. So that was the reason why we discussed n-gram. Uh, Now that I hope, again, I hope that people understand that probability is not a boring, you know, subject or discipline. There is a lot of practical applications, and probability can be fun too. I hope with naive Bayes and n-gram, uh, that point would have been sufficiently driven into our heads. So having said that, now we're going to plunge into what is called as logistic regression. Uh, this is something that I wouldn't want to do in one session, maybe not two, perhaps three. I don't know. It depends on how we progress with logistic regression. So one of the reasons why I would want this to be done in at depth is because these are building blocks of neural networks. So if you understand logistic regression well, you're inching one step closer towards understanding neural networks. And take it, folks, take this from me. I still kick myself for not taking the neural networks course seriously when I was in college. I still kick myself for not taking it seriously because it was part of the coursework. I did electronics and communication. I was lucky to have neural networks as part of my coursework, but I didn't take it seriously because at that point in time, nobody told that I could do, interesting stuff with neural networks. Uh, but it's extremely, extremely important because from what I understand, again, I'm also a student here, so you don't need to take me at face value. You can Google it up and check for yourself. But from what I hear, all these LLM models that we keep hearing about, the chat GPTs of the world, are all fundamentally neural network based models. So it's extremely important for us to understand neural networks. And the bad news about neural networks is it's so complex at one stage that you don't even know why it works. All right. Uh, it gets intensely mathematical at some stage. So mathematical that you're just going to deal with uh, a lot of equations, inputs, outputs, and you just trust the model to work for you. It does. It's not that it doesn't, but it gets intensely mathematical. That's the bad news about neural networks, but it does a lot of interesting stuff, which is why it has got really, really popular over the years. So logistic regression is the building block to understanding neural networks. So just pay a lot of attention to this. Uh, I'm also trying to grapple my head over logistic regression so that the transition to neural networks is much easier. Okay, so let's get started, folks. All right, so before we jump into logistic regression, I'll I'll give a brief introduction to random variables. Of course, this is something which comes from the world of probability. We'll do it at certain depth when we again go back to probability. See, I keep transitioning between the basic fundamentals, like, we did a little bit of linear algebra, then we did a little bit of probability. Now I'm jumping to naive Bayes, doing logistic regression. While doing logistic regression, again, I'll touch upon probability. We'll keep juggling between concepts, so that we just don't uh, spend a lot of time doing just theoretical stuff, right? Just theoretical mathematics. So that's the reason why I keep, jumping between pure mathematical concepts and their applications. But here we need to understand what a random variable is. So I'll give a brief introduction. Uh, Follow me closely, and if you don't understand, feel free to ask questions. All right, so here we go. Again, axiomatic way of looking at probability. An experiment is conducted, results in a certain set of outcomes. So here you go, W1, W2 are all the outcomes. Again, I'll keep asking these questions again and again so that it's wired into our brains. Question number one, are these outcomes mutually exclusive?
Yes.
All right, yes, it is. Because by definition, outcomes are mutually exclusive, right? Look at it this way. If you go to chemistry, for instance, think of these outcomes as atoms, right? One way to look at outcomes are atoms. So a hydrogen atom is not an oxygen atom. It's not the same as a carbon atom. They're all different atoms, all right? Look at it that way. Now, an event is it's a subset of the sample space. Question, if I have two events, is it necessary that they are mutually exclusive? Or is there a possibility where two events can have something in common?
It is
Well,
not necessary that they should be mutually exclusive.
exactly. It's not necessary. They could have something in common. For example, I roll a die. The outcomes are 1, 2, 3, 4, 5, 6. Certainly, they are mutually exclusive. I can define an event E, which is a multiple of, say, 3. That's event E. Or let's say call it E1. I can have another event E2, which I can define as even numbers. So of course, evidently, you can see that the number 6 is an outcome which is common between E1 and E2. So clearly, if you take two events, it doesn't mean that they are mutually exclusive, but they could be mutually exclusive. All right, it depends. The probability of an event is nothing but, here we go. Look at this. Can somebody tell me what are we doing here? Why is it that it's a simple summation of P of W, where W belongs to E? So what exactly is happening here? Can somebody help me interpret this mathematical notation?
Since the events are independent, we are adding.
Be very careful. Be very careful in usage of words. Did we ever use the word independent anywhere so far? Be very careful, folks. I didn't even use the word independent anywhere so far, right? Give me a moment. So what do we have here? So we need P of E is equal to, I still struggle with this. I don't know why. Sometimes it works, sometimes it doesn't. Sigma P of W, where W belongs to E. Now this is the expression, the mathematical notation. I want somebody to interpret this for me.
Okay, omega is the set of outcomes of the event E.
Okay, so let's say E is the event and the outcomes are omega 1, omega 2. Is this omega or is it W? Is it omega, is it? I'm just trying to recollect. Is this symbol omega, folks? I'm just trying to recollect. Is that omega? Okay, let's say it's omega. Doesn't matter. Just a name. All right, so let's say it's omega 1, omega 2, omega 3. Go ahead. Abhinav. So what does this mean? Why are we summing up here? So this means, so let's
Is
expand this. So what you're saying is, correct me if I'm wrong, it's P of W1 plus P of W2 plus or omega 2, okay? Omega 3. All right? This is what this means, right? Now, how is it that we managed to sum this up? Why is it that P of E is the sum of P of, as you
okay,
call it,
P of
omega 1, omega 2 plus omega 3? Why is it so?
um, there are three possible outcomes in the event T.
Okay.
So for the event E should be occurring, we are adding those three, right? So
Why adding? That's my question. Yes, you're adding, you're right, but why adding? Go one level deeper. Why adding? Why didn't I
it's an odd,
multiply? Why didn't I
odd.
add these two and then subtract W3? Why didn't I do this, right? Something like P of W1 plus P of W2 minus P of W3. Why didn't I do that? When can I add? That's my question. When can I add like this? If these are outcomes, when can I add? When they are?
Mutual exclusive.
Exactly. You can add, always remember, folks, you can add when they are mutually exclusive. And we know by definition, okay, by definition, outcomes are mutually exclusive, right? So since by definition, outcomes are mutually exclusive, I can just add P of W1 plus P of W2 plus P of W3, okay? And this whole, I mean, instead of writing it this way, notationally, in simple mathematics, this is how it is represented. Sigma P of, I'm calling it W, call it omega, whatever, where W is, where W belongs to E, where E is the event, all right? So now, what is a random variable? Okay, extremely important. I'll read a definition for you. A random variable is a variable that takes a random value. This is how random variables are unfortunately introduced in college. Well, what does it supposed to mean? When you say a random variable is a variable that takes a random value or takes on random values. The question is, where is this randomness coming from? So when you're calling a variable random variable, where is this randomness coming from? So for example, you go to algebra, simple algebra, all right? So we define variables such as say x, y, z to represent say numbers. Do we ever call this random variables? In class 6, we would have been introduced to algebra, right? Did they ever call x, y, z as random variables?
No,
They
no,
just
we
called it
call
as
them variables.
variables, correct? So why call this? Then what is this random variable all about? Where is that randomness coming from? What do you think? Any thoughts, folks? Where is that randomness coming from? All right, it's not particularly easy, so let me explain. Read this last line. To make the notion of random variable precise, we define it. Okay, we'll correct the spelling. We define it as a function mapping the sample space to the real line. This is the precise definition. Okay. Now, what the hell is this supposed to mean? A function mapping the sample space to the real line. Okay. Let's understand what it means. Let's take this case. Okay. You've conducted an experiment. The experiment results in outcomes. So here are the outcomes here. S1, S2, S3, S4, S5, S6. So for example, let's do an experiment. The experiment is rolling a die. So can you tell me what are the outcomes? Someone? What are the outcomes? I roll a die once. What are the outcomes of the experiment, folks?
1, 2, 3, 4, 5, 6.
Sorry?
1, 2, 3, 4, 5, 6.
That's right. So 1, 2, 3, 4, 5, 6. All right. Now, of course, in this case, it turned out to be a numeric. Let's do one thing. Let's say I toss a coin. Then what are the outcomes?
Heads and tails.
Heads and tails. Okay, that's simple. I want to show both. All right. So here's a sample space. In this case, the sample space was a bunch of numeric. It was numeric in nature. Here, of course, the sample space is not numeric. All right. Now, what a random variable is it is a function that maps. It's a function that maps the sample space to some number on the real line. So think of remember the number line, folks? From minus infinity to infinity. So what a random variable does is it basically maps the outcome of an experiment, the sample space basically, to the number line. Okay. Now, what is it supposed to mean? For example, let us say I define this function. I take this experiment, okay? And I define the function as the outcome multiply. Okay, let me put it this way. Okay, the outcome is divided by 2, and I take the remainder. All right, let's say that's the function. So I define a random variable. I'm calling this random variable as say f. So, or maybe I'll call it say x. Okay, here is a random variable x. How do I define x? I take the outcome of this experiment. I divide it by 2 and find the remainder. Okay. Now, can somebody tell me what values can x take? take this experiment. Outcomes are 1, 2, 3, 4, 5, 6. How do I define x? X is a random variable.
1 or 0.
Sorry, 1 and 0. That is right. Okay. X can take only two values. Why? When I divide these outcomes, 1, 2, 3, 4, 5, 6, forget the outcomes. Any number when I divide by 2, and if I want to get the remainder, there can only be two possibilities, right? I can either get a 0 or I can get a 1. Of course, I'm assuming the outcomes are integers here, right? So x can take a value of 0 and 1. These are the only two values x can take, right? Now the question is, I have defined x as a random variable. And as I said, that random variable can take two values, 0 and 1. Now let me ask this question. If I want to figure out the probability of x taking the value of 0, how do I figure it out? How do I figure it out? So when faced with that question, right, always remember, folks, remember a random variable takes a value. That's right. But don't forget, this randomness comes from the outcome. So first step is to map this to outcomes. What are the outcomes, folks? What are the outcomes? If x has to be 0, then what are the outcomes? Then outcome has to be 2,
4, 6.
4, 6. Correct? Do you agree? So what is the probability of, so I can define this as the event as, so x equal to 0 can be translated as an event. I'm still struggling with this pretty much. Event 2, 4, 6, correct? The occurrence of 2, 4, 6 as outcomes would mean x is equal to 0. Now, can you tell me what is the probability of 2, 4, 6? Each one of them is an outcome. Can we say this is probability of 2 plus probability of 4 plus probability of 6? Would you agree? Why? Because each of these are outcomes, and outcomes are mutually exclusive. Correct. There's a plus there. Okay. And we know this is nothing but 1 by 6 plus 1 by 6 plus 1 by 6. So that's 1 by 3. All right. Now let's do the other problem. I'll
1 by
delete this.
2, right?
I'm sorry. Apologies. 1 by 2. Okay. Let's do the other problem. I'm going to define so here is the outcome, head or tail. Okay. So now we need a function. As I said, a random variable is a function that maps the outcome to the real line. It has to map some function. Okay. Now I can define any function. So for example, I can say if head is equal to, if head, then 150. If tail, then 100. As simple as that. So if it is head, I map it to the number 150. If it is tail, I map it to the number 100, or let's say minus 100. Okay. For example, let's say this is a game. We play a game. The game is as follows. I toss a coin. If a head throws up, then I will get 150 from you. If a tail throws up, then I will give you 100. Something like that. Right? So I've defined the outcome. Outcomes, of course, are H and T. But now I have a random variable. I'm just going to call this random variable again x. X can take a value of 150 if head throws up. X can take a value of -100 when t throws up. All right. Now let me ask a question. What is the probability of x is equal to 125? Remember, try to figure out, is there a way to map this number on the number line to an event, to an outcome rather. Forget event, let's call that outcome for the moment. Is there a way to map this to an outcome? Can you map this to an outcome?
No.
You can't, correct? There's no way you can map this to the outcome, right? So which means what is this probability? So basically we are saying this is probability of the event being a null set, correct? Why null? You can't map this. X equal to 125 can't be mapped to any event. So this is 0. Now let's do another problem. Probability of x is equal to 150. Assume this to be a fair coin, okay? So what is this? I'll have to map it to an event. Can I map it to an event, folks? I can, right? Where the event is equal to what? Can I say
Heads.
this is heads, correct? So now I know this probability. Assuming it's a fair coin, 1/2, correct? Now, probability of x is equal to -100. Now, can somebody tell me? Again, the event would be tail, correct? Would you agree? Because I said if x equal to t, then -100. So what is the probability now? Can we say this is again? If it's a fair
1/2.
coin, it's again half. Sorry, folks. Now, I have a question for you. Think about it. I said this was a game, right? It's a game that I and you are going to play. And the rules are simple. If it throws up a head, I get 150 from you, which is why I say x equal to 150. X basically denotes how much money I get, okay, in the game. So I toss a coin. If a head throws up, I get 150. If a tail throws up, then I give you 100. Okay, that's the game. All right. So the first thing I do is I ask you, come on, shall we play this game? Okay. And the game is such that we're going to play this game a lot of times. Say 1,000 times or maybe 10,000 times. Would you want to play this game? Or not? I'm giving you the choice. Before entering the game, I'm giving you a choice. Whether you want to play this game or not.
If it's a typical fair coin, then yes.
Why yes?
Because we'll gain. Right.
No. I'm talking about you, not me. X is a random variable where I get 150. I get 150 when a head throws up, which means you're going to pay me that 150. All right.
Yeah, then I
Tail,
won't play.
you won't play, correct? But if you have to structure it properly, can we do it this way? Let me just see if I can use an eraser. Ruler. All right, I hope this works. Okay, now let's structure this problem in a way where it helps you to understand how does it look for you. Okay. Now, can I define a new random variable y? This random variable is nothing but it is the variable from your perspective. Okay. If head, what will happen in this case?
Minus 150.
Exactly. If it is tail,
Then gain plus 150. Plus
plus
100.
plus
100.
100. Okay. So now let's do the same thing. Probability of y is equal to minus 150 is equal to what?
1/2.
1 by 2, correct. Probability of y is equal to plus 100 is equal to, again,
1/2.
1 by 2, right? Now, when you decide whether to play the game or not, the way you do that is you're saying, look, if I play, for example, let's say I played 10,000 times, okay? Sorry. Excuse me. So let's say I play this game 10,000 times. So evidently 5,000 times I will get a head and 5,000 times I will get a tail. How did we get that? Anyone? How did I get this number? I said if we play the game 10,000 times, how did I get that I'll get 5,000 heads and 5,000 tails?
50%, right?
Yeah, that's because of
50%.
this probability, isn't it? All right.
Probability of this one
So
by
it's
2.
like saying y is equal to, okay, this sucks. Okay, minus 150. And then here y is equal to plus 100. All right. So if I play the game 10,000 times, 5,000 times y would be minus 150. 5,000 times y would be 100. So can't I figure out how much money I'll make? I'll make 5,000 multiplied by minus 150 and then 5,000 multiplied by plus 100. And if you sum it up, you'll find that it's negative for you, of course. When I say that, I'm talking from your perspective here. All right. So evidently, you will not choose this game. All right. I'm jumping the gun here. This is what is called as expectation of a random variable. Okay. We'll do expectations separately, but this is what expectation means basically. Anyways, so hopefully you have an inkling of what a random variable is. So let's do the uh, the definitions again. So S1, S2, S3, S6 are outcomes of an experiment. In this case, 1, 2, 4 are numbers on the real line. So here we go. These are numbers that we find on the real line. And the arrows denote a mapping between the outcomes on the real line, real number line. So which means S1 is mapped to 1, so on and so forth. Okay. Now, question. Can the same outcome, or rather, let me put it this way. Yeah, can the same outcome be mapped to different numbers on the real line? You understood the question? Can the same outcome, say S1, be mapped to different numbers on the real line? Would it make sense to do that? You understood my question, folks? Here is an outcome. Let's say this is the outcome. Can I map this number, this outcome, to different numbers on the real line? What is your
No,
intuition?
because we cannot have multiple outcomes for
Sorry, say that again. You cannot have what?
multiple outcomes for one function.
Okay, so what you're saying is I cannot map the same outcome to different numbers on the real line. That's what you're trying to say. So for example, all right, let me flip it where I ask the question. I take a number on the real line, okay? Can two different outcomes be mapped to the same number on the real line? So if you look at this, I mean, just have a look at this diagram and you can tell me, can the same, or let me put it this way, can two different outcomes be mapped to the same number on the real line?
Yes.
Yes.
Of course it can be. So you can have a situation where, here we go, S1 and S2 can be mapped to 1, okay? In this case, can somebody tell me what are the outcomes that are mapped to 1? Sorry, give me a moment. What are the outcomes that are mapped to the number 1 on the real line?
S1, S5, S6.
S1, S5,
S3,
sorry, S1, S3, okay.
S6.
S1, S3, S6, okay. So can I ask a question now? So I'm going to call this X is a random variable here, right? So my question is, if I have to know what is the probability of X is equal to 1, how do I figure it out? What is the probability that the random variable X takes the value of 1? How do I figure it out? Of course, I don't have the exact numbers, but tell me the approach. How would I figure it out?
P of S1 plus P of S3 plus P of S.
Okay, so step by step. So first step is you have the random variable. What do you do next? Map it to outcomes, correct? Always, that's what you're going to do. So you're going to map it to outcomes. What are the outcomes? It's a probability of, let's go back. What are the outcomes here, folks? S1, S3, and S5. Am I right? So can we say this is probability of the outcome being S1 or S3 or S5? Question, are these mutually exclusive? Yes, by definition. Outcomes are always mutually exclusive. Get that right into your head. And now that they're mutually exclusive, I can write this as probability of S1 plus probability of S2. Sorry, somebody is talking. Please mute yourself. S3, unless you have a question. All right. So this is how you can write it. So I can say probability of X1 is equal to probability of S1. So when I say probability of S1, what does it mean? Probability of getting the outcome S1. This is probability of getting the outcome S2. This is the probability of getting the outcome S3. All right. Let's do one more. Can somebody tell me what is the probability of the random variable X taking a value of 0?
S2, S4.
S2,
1 by 4.
S4. That's right. Sorry, 1 by what? Sorry, Abhinav, you're saying something. Here,
No,
outcomes
you
are not
see, I
equally
thought
likely.
for
It's not equally likely,
that's
right? Okay.
I
So
noticed.
you're right. Rahul is right. So P of give me a moment. I don't know.
Sir, for H is equal to 1 is not S5, it's S6.
S6 is
For
it?
H
Let's
is
see. Oh yeah, you're right. You're right. S6, and then yeah, correct. S5 is 4. Correct. You're right. So this should actually be. I don't know what happened to my. This whole thing is getting so sensitive. Anyways, so you're right. Let's change that. Sorry. There's a razor. This shouldn't be S5. This should be. This is also wrong. Sorry. Let me change this. So this is S1. S2 is mapping to 0. I'm sorry. So it's S1, S6, and S3. Correct? Am I right? If you look at this, S1 maps to 1, S3 maps to 1, and S6 maps to 1. So let me change this. I was wrong. So this is S1. Let me just go to. This is S6. All right. Now probability of, we're trying to calculate probability of X is equal to 0. Now tell me what are the outcomes?
2 and 4.
Okay, so that will be S2, comma S4. So that's evidently probability of S2 plus probability of S4. All right. Okay, cool. Now that's your basic idea of random variables, folks. All right. So let's do one distribution. This is sufficient for logistic regression. And this distribution is called the Bernoulli distribution. It is what is called as a toy distribution, a toy model, but it's very, very useful. Okay. So here we go. A random variable X is said to be Bernoulli P, which means a random variable X follows the Bernoulli distribution if it has the following probability mass function. Don't worry too much about what a probability mass function is. It's basically a mapping between, it's nothing but you have the random variable. In this case, the random variable can take two values, 1 and 0. All right. If it takes a value of 1, the probability of X taking a value of 1 is P. The probability of X taking a value of 0 is 1 minus P. And what this means, can anybody tell me?
If X is anything other than 0 or 1, then it will be 0.
Exactly. All right. So let me take a very simple example. So let's say elections in the United States. All right. So there's a political party. a political party wins or loses. One of the two can happen. All right. Now, my question is, can we define, of course, this is random, right? Why it is random? Because one can't say whether a political party would win or lose. So certainly it is random. Can we define a random variable? Of course, we'll have to define see, remember folks, when we define random variable, it is always mapped to a real line. So let's say I define a random variable x, which can take a value of 1, which means, let's say, they win. Then the same random variable can take a value of 0, which means, let's say, they lose. All right. Now, can this random variable take any other value other than 0 and 1? Can it?
No.
No.
No, it can't. Correct. And let's say the probability of win is P. Then what is the probability of loss? Assuming 1 minus P. Let's assume there's no possibility of tie and all that. Okay. Typically in elections, there are no ties. So the probability of win is P. The probability of the political party losing is 1 minus P. So here we go. In this particular case, I have modeled the election of a political party as a Bernoulli distribution. All right. Now, there is another way to represent this distribution, which is the following. Okay, here we go. Give me a moment. Here is a way to represent the same distribution. Can somebody tell me, or rather, can somebody help me out? How is this exactly the same as the one above? This is very useful. This way of representation, it's called the multiplicative form of the Bernoulli distribution. But can somebody tell me, how is this exactly the same as the one above? Just look at it, use your pen and paper, and tell me, how is this same as this?
So when we substitute it as 0,
Okay.
we arrive at 1 minus, and we substitute x is equal to 1, we arrive at p, so it works.
Okay, wait. So I'll snip it. Let's do it. Sorry, folks. Let's snip it again. So let me paste it on a whiteboard, and then let's see. Okay, so here we go. Can apart from Abhinav gave us an answer, but can somebody? So let's say x is equal to 1. What happens? So P of x is equal to 1 is equal to, can somebody go through this expression and tell me? What would that be?
One,
Sorry, louder. I didn't understand.
you have to substitute,
Your internet is
you have
very
to
poor,
substitute the
Abhinav.
value
I
x
can't
is
hear
1.
you properly, Abhinav. Someone else, folks, with better internet.
P.
Okay, how is it P?
If we substitute x is equal to 1, p to the power of 1 is p.
Okay.
1 minus 1, it's 0. Anything power 0 is 1.
Okay, so P to the power of x. X is 1, so this is P. 1 minus p to the power of 1 minus
1
1.
minus
So that's
1,
0.
0.
So anything to the power of 0 is
This 1.
1. So this is p. All right. Then p x is equal to 0. Plug. Can somebody plug in?
P to the power of 0 is 1.
Okay, p to the power of 0 is 1. And this is
1 minus p, that's all.
1
To
minus
the
p
power of
whole to the
1.
power of 1. Correct?
1.
So this is 1 minus p. All right. And what does this say? Anything other than 0 and 1, this probability is 0. Correct? So if you look at this representation of Bernoulli distribution, it is exactly the same as this representation. There's no difference. Now, one might be wondering, why are we using this? It's very useful. You'll understand why. In the logistic regression world, when we compute the loss function, we'll come to that when we get there. We will be using this form of Bernoulli distribution. All right. Now, with that in place, let's get to logistic regression basics. As always, folks, we have a hard stop at 12, so don't worry. We'll take multiple sessions to cover this. So let's get to the basics of what exactly is logistic regression. Okay. Now, in our naive Bayes world, so let's say, again, we go to this world where we're trying to figure out the sentiment. So you have positive sentiment and negative sentiment. You have a document. So let's say the entire thing is a document here. This is one document. And we're trying to associate a sentiment with this document. Okay. Now I'm going to the naive Bayes world. We modeled such problems before. Let's just focus on the document. So what was a feature in the naive Bayes world? How did we define features in the naive Bayes world? Wasn't each word a feature? Remember, folks? We took each word and then that became a feature for us. Now what I'm going to do now is, and of course, in the naive Bayes world, what happened was we had this crazy, I shouldn't call it crazy, but we had this assumption that all these words are independent of each other, which means when I express positive sentiment, and let's say I use the word fantastic and lovely, naive Bayes assumed that I can use these words independently, but we know it's not the case. When I use the word fantastic, I would also tend to use the word lovely. But naive Bayes went with the assumption that they're independent. Okay. Now let us say I don't want to do any of those. And I create my own set of features. I'm calling that as variables here, VAR. And I've defined 6 variables here. All right. So let's see what these 6 variables are. Follow this very carefully. Okay. The first variable is a count of positive lexicon words that belongs to the document. So here's a document. So what does this do? This basically looks at the positive words in the document and counts. So in this case, if you look at it, 3 words, there is enjoyable, there is nice, and then there is great. I take the count of them. X2 is another variable. It's a count of negative lexicon words, which means it picks up the negative words in the document and then counts them. So here there's hokey and there is secondary. These are 2 negative, words with negative connotation. So X2 is 2. Then X3 is another variable where it's a binary variable. Can somebody tell me why is it a binary variable?
It
Why
can
is
take
x3
only
binary?
two values, 0 or
Exactly.
1.
Exactly. So x3, if you look at it, it can take only two values, 0 or 1. And the way it takes these values is as follows. If the word no figures in the document, then it takes a value of 1. If the word no doesn't figure in the document, it takes a value of 0. X4 is another variable which takes the count of the first and the second pronouns in the document. So here we go. So there is X4. Where is X4? X3, X2. Here we go. I, me, and you. So it takes the count of the first and the second pronouns in the document. That's X4 for you. And it takes a value of 3 because there were 3 first and second pronouns in the document. Abhinav, I don't want you to answer. X5, is that a binary variable? Anyone? I just want to wake people up.
Yes.
All right. It is a binary variable, correct? Because it can take a value of 1 and 0. So here it's simple. If there is an exclamatory mark anywhere in the document, X5 takes a value of 1. If there is no exclamatory mark anywhere in the document, it takes a value of 0. And finally, X6 is a variable which just takes the ln. You know what a ln is, right? What is the base of ln? Can somebody tell me? Not Abhinav. Someone else. I know you can answer Abhinav. Someone else. The base of ln. You know what I mean by base of ln? Log, you know, ln means ln here, which is log to the base what?
2.
E, correct. Exactly. Not 2. It's E. All right. So whenever we use the, this mathematical symbol ln, it means it's log to the base E, which is 2.71 whatever. All right. So what are we doing here? X6 is another variable that calculates the ln of the number of words in the document. All right. Now, of course, you can ask this question, why the hell are we doing all this? Why are these variables popping up from nowhere? Right. Let us say I come up, I think all these words, all these variables convey some sentiment. Let's say I have this intuition. All right. And I come up with this lovely or ugly, whatever it is, set of variables. All right. Now, let's move to the left. Logistic regression is a probabilistic classifier. Just as naive Bayes is, logistic regression is also a probabilistic classifier. Okay, I use the word classifier. What does a classifier mean? What does classifier mean? What is you can try to explain that in simple English, but what does classifier mean?
So to classify it as something, maybe it can be a
Okay,
cat, a dog.
but what is a classifier?
So it's something which does the classification.
Okay, can we say a classifier is something like a function that takes
Yeah,
features as an
it
input,
takes the
right?
and gives us
And
the
then it
class.
classifies the data to, in this case, we
Yeah,
work with binary classifiers where it classifies it as a positive sentiment or negative sentiment, correct? So imagine, so when we use the word classifier, imagine that to be like a function. In this case, this is a logistic regression function that takes in data. In this case, the data is x1, x2, x3, x4, x5, x6. That's what the logistic regression function takes in as inputs in this case. And then The output is, it tends to classify it as positive or negative sentiment. That's the whole idea, folks. All right. So VAR are features. Note these are not words anymore. Unlike in naive Bayes' world, where each feature was a word, here you're coming up with very interesting kind of variables or features, counts, and then you're looking at whether there's a no in the document or not. Even the length of the document, the word count of the document is a feature here. All right. Then what do? We combine these features in certain weights to compute the sentiment that is conveyed by that paragraph. So you take these features, multiply them by some of these weights, some weights. Okay. I'm calling that as W. And then you get an output, a number. All right. And it conveys a sentiment of the paragraph. Question: the weights, are they scalars? Do they look, this weight W, does that look like a scalar or does that look like a vector? Is W a scalar or a vector? Is it so difficult to say?
Vector.
Okay, Abhinav says it's a vector. Someone else. Does W look like a scalar or does it look like a vector? I'm not going to proceed here unless I get an answer.
Vector.
All right, you say it's a vector.
It's vector
Why?
because
Okay, go ahead.
it's
Go
a
ahead.
vector because it has both mass.
Oh, no. Where is the mass? There's no mass here.
No.
Don't bring in physics here. There's no physical interpretation to this. Madhumita, why is this a vector? Why is W a vector?
Because it has both positive and negative values.
Is that the reason why it is a vector? So let's say they were all positive. Does that mean it's not a vector? What is a vector?
It has both
A list
magnitude.
of numbers. A
That's
list of
it.
some.
That's it. Nothing more. It's a collection of numbers. It's a list of numbers, right? I mean, in our world, of course, it could be a list of letters. It could be whatever, right? So in this case, it's a list of numbers. Now, how many elements are there in this vector? Can somebody tell me?
6.
6. Now, why are there 6 elements in the vector? Why not 7? Why not 8?
We have 6 variables.
Exactly. There are 6 features here, right? X1, X2, X3, X4, X5, and X6. Remember what I said? These are features or variables. Taking this count, 3, 2, 1, 3, 0, and then whatever. We combine them in a certain weight, some combination. And that is W. So for example, you combine the first variable with 2.5. You combine the second variable x2 with the number -5. So on and so forth. Can somebody tell me intuitively, why is x1 positive and why is x2 negative? I mean, when I say that, the weight of x1, let me correct myself. Why is the weight of x1 positive and why is the weight of x2 negative? There's a reason why this is positive and this is negative. Can somebody think and tell me? Remember, folks, what is the objective of this? I mean, this whole model that we're trying to build? We're trying to build a model to figure out the sentiment. All right. Just remember that. Keeping that in mind, why is the weight of x1 positive and why is the weight of x2 negative?
Is it because x1 is the count of positive lexicon words and x2 is the count of
Exactly.
negative lexicon words?
Exactly. So if you have a lot of positive words, then you have a positive weight here to make sure that you add to that positive sentiment. All right. If you have a lot of negative words in the document, then you have a negative weight so that pulls down the positive sentiment. All right. And likewise, if you look at x3's weight, it is negative 1.2. Negative 1.2. Can you tell me why? Just use your intuition. Why is x3's weight negative 1.2?
X3 is the count of the word no.
It's not a count. Remember, it's a binary variable, right? Where does it say it's a count? Does it say it's a count?
If the word no
So
is present in the
x3 is
document,
not
it's
to be
1.
taken into count.
Why?
So the weightage given to x3 is very low, so that we don't have to actually take the thing in calculating our progress
Is it that
processing.
low? The others are even lower. Look, there's a 0.5, there's a negative 0.7, right? But can you think of another reason? Can't we interpret the word no as a negative sentiment? It carries a negative sentiment, isn't it? Right? Would you agree? When you have a
Yes, we see.
so the occurrence of the word no carries a negative sentiment, which is why the weight is negative 1.2. All right. I'm not too sure about x4 and x6. Why x4 has a positive weight and x6 has a negative weight. I didn't think too much about it, but I hope you guys understand what these weights actually mean now. All right. Now let's do one thing. Okay. Let's say we multiply the weights with the values of these variables. Okay. Multiply the weights with the values of these variables. So what is that number? Can somebody calculate it for me? I'm going to wake you up now. Use an Excel. Just multiply the weights and the value of these variables. This, by the way, is 4.19. Okay. Or at least take a guess, folks. Somewhere close to whatever, blah, blah, blah. Is somebody doing the calculation?
Yes, we see.
All right, go ahead. Okay, if does it take so long?
I got 12.86.
Check, 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 check again. Wait. Let's do this. Okay. Give me a moment.
Is that minus 5.13?
I get a different number. I get, okay, wait. I've added an additional 0.1. I get 0.733. Just check this, folks. You took 3, 2, 1, 3, 0, and 4.19, 18 or whatever, right? Correct? 3, 2, 1, 3, 0, 4. Of course, I calculated ln of 66, which is 4.18. And then the weights are 2.5, -5, -1.2. Don't forget. 0.5, 2. Oh, I'm sorry. This should be 0.7. Okay, I'll modify that. Not -0.7, it's just 0.7. Okay. Now, what do you get? Do you get something like this?
0.733.
All right, wonderful. Okay. So if you multiply the weights and this value, you get 0.733. When you did that, W multiplied by these X values, if you have to represent that operation in the world of vector algebra, what is that operation?
Dot product?
Exactly. So that's a dot product, correct? Why? Because you can imagine this to be a vector. Let's call that as X vector that comprises of these values 3, 2, 1, 3, 0, 4.19. So that's your X vector. Here is your W vector. So you take W vector, X vector, calculate a dot product. Okay. And that dot product is equal to 0.733. Then what we do is assuming even if all of these were to be 0, we have something called as a bias. Okay. It is like saying, look, I have a document that is not conveying anything positive, anything negative very clearly, but do I consider that as a positive thing or a negative thing? Is that a positive sentiment or a negative sentiment? Or maybe it doesn't carry any sentiment at all, right? So let us say I have a text that doesn't have, it has all of these as, of course, forget this value. A text will have a count, all right? But let's say hypothetically, all of them are 0. And even then, if I think that that conveys a positive sentiment, then this scalar quantity, call it as bias, it adds to the sentiment. Now, I can also say if there is, if all of these are 0, then I can say, look, that conveys a negative sentiment, in which case this could be negative. Instead of plus 0.1, it could be a minus 0.1. Okay. So let us say in this particular case, it conveys a minor positive sentiment by default. All right. So what are we doing here? We have W vector, you have X vector, you calculated the dot product. Can somebody tell me how is it that this expression works? W is a vector, X is a vector, and then I add a B. Can I do that? Why does that work?
Dot product of two vectors is a scalar.
Exactly. So this is a scalar, and B is of course a scalar because it's a number, like say 0.1, 0.3, whatever. So which means W dot X, the dot product of W and X plus B is a scalar too. All right. Now, when you calculate this, you get this number. Here we go. 0.832 or 833. That's the number that you get. All right. Now if you think about it, I can say that this probably conveys a positive sentiment. So the way I'll play around with, I'll do this. So for example, let's take this row. Can somebody tell me what is the difference between the first row? And when I say first row, I mean this row and this row. What's the difference? What's the difference between this row and this row?
X2 is increased by 1.
Correct. So which means if I have to put that in plain English, is what this represents some document. Would you agree? We don't know what document it is, but this represents some document. This represents another document. Does this carry more negative sentiment compared to this? Or does this carry more positive sentiment compared to this document?
Negative sentiment.
Okay, why?
Because the count of negative is increased.
Exactly, right? Correct. Absolutely, right? Now, if you look at w dot x plus b, it says the same thing. You see that? This is negative 4.16 and that is 0.83. So this expression w dot x plus b, it does help us to, that number that you get does help us to figure out whether the document carries a positive sentiment or, whether the document carries a negative sentiment. Let's do one more thing. Let's take this row and this row. Forget the calculation w dot x plus b. My question would be in relation, or rather when compared with this row, or rather, let's say this is document 1 and this is document 2. The question here is, compared to document 1, does document 2 carry more positive sentiment or negative sentiment?
More negative sentiment.
Okay, relatively negative. Why relatively negative?
The positive count of X1 is
exactly.
decreased by 1.
Even though the count of negative is the same and the rest is all the same, if you look at the count of positive words, it has decreased from 3 to 2. Now let's look at this expression, this number here. W dot x plus b is 0.83 and here it is negative 1.66. All right. So evidently we can see that this is conveying some negative sentiment as compared to this document. All right. Now, if you think about it, this w dot x plus b, what could be the range of this expression? What could be the range? W dot x plus b. What could be the range? You understand my question? I just took some value. So let's say I plug in, I'll do another thing, okay? So that you understand what I'm talking about. So let us say I plug in, I'm not going to change this. I'm going to keep this as 3. I'm going to change this as say 50, 1, 3, 0. All right. And this of course is the same. Here we go. This is w dot x plus b. Let me do one more. I'll change the count of positive, say 300, right? It's a bad idea because this will also change. Because if this is 50, this can't be the same, but let's say it is the same, okay? I'm making it easy for us to calculate, okay? Now, folks, tell me, what can be the range of W dot X plus B? Just use your intuition, folks. What can be the range of
-infinity to
this
plus
W dot?
infinity.
Yeah, who was that?
Madhumita.
Madhumita, you're right. It can actually go from minus infinity to plus infinity. Don't you see that, folks? Right? Now, let me ask a question. I'm going to add 2 more rows here. 299, 298. Okay. I'm going to ask a question here. Take these 3 rows. Do these 3 rows, or other 3 documents, because each row represents a document, do these 3 documents convey a positive sentiment? Do they? Yes or no?
Yes.
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 Would you really care that this number is 743 and this is 740 and this is 738? Would you really care? Or you would
No.
just say, come on, it carries a positive sentiment. What's the big deal? Because remember, we're doing classification, folks, right? Our objective is not to say, see, when I say something is positive and something is negative, I'm not bothered about the extent of positiveness or the extent of negativeness. That's never the question here. The classification problem is simple. I call a document a positive document, or rather a document that carries a positive sentiment, and I call a document as a document that carries a negative sentiment. Nothing more. There's no grade of positivity. There is no grade of negativity. That's not our concern. Given that, here are 3 documents, 300, 299, and 298. And this is the product of W dot X, the dot product of W dot X, or rather the dot product of W and X plus B, all right? And here are the 3 numbers. My question is, would you care that this is 743, this is 740, and this is 738? Would you? Or would you not?
No, we don't care.
You don't care. Wouldn't you want to say, okay, all this is positive, man. Come on. That's sufficient, correct? So let's say I denote positive as 1, okay? I'm happy, isn't it? I'm just calling this 1. Let me do one more thing now, okay? I'll take this. Go to the other side. I'll make it, say, 200. 199, 198. Okay. Now, 3 more documents. Do they carry negative sentiment? These 3 documents?
Yes.
All right, they do. Here are the numbers. Again, given the problem statement where we don't care about the extent of negativeness in the document, would we be particularly bothered about the differences that we see here in Z? Z is, of course, W dot X plus B. Would you care about the difference in the negativeness in these three documents? Or would you just say, come on, these are negative documents? Again, and I'm talking in from the context of the problem, which is merely to classify the document as positive and negative. The grade doesn't matter. Now tell me, would we care that there is a difference in negativeness between these three documents?
No, VC.
No.
No, correct? So can't I say this is 0? So basically what I've done here is I'm converting this whole thing intuitively into something binary, 1 and 0, correct? 1 means it's positive, 0 means it's negative. All right. What we are trying to do here is we are trying to move these numbers into a scale of 1 to 0. All right. So that if the number is closer to 1, I can say it's positive. If the number is closer to 0, of course, in this case, I didn't tell you how I got that 1. We'll come to that. Okay. I didn't tell you how we got that 0. Intuitively, we're just putting a 1 and a 0. All right. But let's say there is another, let's say this case itself. Instead of 1 and 0, I can put a number like 0.69 there, which is closer to 1. So it's like saying this is more positive than negative. I can say that. All right. But just leave that for the moment. But look at it this way. Here we have these crazy numbers. And what we're trying to do is we're trying to convert these crazy numbers, which can extend from minus infinity to infinity. You're trying to compress that into the scale of 1 to, or rather 0 to 1. All right. And there is a lovely function that allows you to do that, which is what is called as the sigmoid function. We'll come to that in the next session, but look at this graph, folks. This is the graph of a sigmoid function. Z is any number. And this expression is 1 by 1 plus e power minus z. And if you look at this, can somebody tell me when z is equal to 6, what is sigma z?
1 by plus
No. Just look at the graph and
minus.
tell me, folks. Just look at the graph.
Okay.
1.
It's close to 1.
Close to 1. Don't you see the moment, z gets close to 4, it closely, not z, I'm sorry. The moment z hits 4, it's getting very, very close to 1. And beyond 4, it's almost 1, correct? Likewise, when z is minus 4, it's close to 0. And any number less than minus 4, it's 0. You don't need to worry. The only area where there is some ambiguity is between minus 2 to 2. You see that? Where, it can, sigma z can vary between, say, somewhere between 0.1 to all the way up to 0.9. So what this function does is it has this ability to beautifully squish something from minus infinity to infinity into the small range of 0 to 1 in such a way that only for a small set of values, that is between minus 2 and 2, there is some ambiguity. Beyond that, if you look at it, the moment you go to 3, 4, it's very, very clear it is 1. Likewise, the moment you go to minus 3, minus 4, it is very clear that it is 0, right? It is only when you have values between minus 2 to 2, there is an element of ambiguity, okay? And this sigmoid function is the one that we will use in logistic regression to compress this z into that range that we talked about, 0 to 1. Okay? We'll continue how we're going to do that in the next session. So we'll take some sample examples and see what the sigmoid function does and how it converts a number such as z, which can extend from minus infinity to a number between 0 and 1. Okay? Any questions, folks? All right. If there aren't any, catch you on Monday. Thank you and have a nice weekend.
Good night, VC.
You too. Bye.